Hello, this is section 2.3 for Calc survey, and today we're going to continue our discussion on derivatives, and we're going to kind of interpret them and talk about some new notation we're going to use for derivatives. So this video having to do with puzzles, we would watch this video in class, and it's of a lady who's putting together a puzzle with all these different zoo animals, and it does the time lapse, and you get to see how, and what we'll talk about in class is certain parts of the puzzle she can put together really fast, as opposed to the background of the puzzle. It takes her a lot longer. So looking at the average time it took her to put the puzzle together isn't a good representation of certain times when she was able to put the zebra together really quickly or the perimeter together really quickly. So that was the discussion we'll have in class. So this says, let the area A in square inches of the puzzle in hours t be represented by the function A equals f of t. Interpret the following. So in this case, f of 42 equals 900. This would mean at 52 hours, she has 900 square inches finished. That's the function. But this, notice this little tick mark here, that's a derivative. So this would represent a rate of change. And notice it's positive, so we know she's completing more and more of the puzzle. She's not taking pieces away. But at 32 hours, we're increasing 5 inches squared per hour. Now, had that been at hour 1, when she was putting the perimeter together, that rate of change is going to be higher. Had this been when she was putting the zebra together, that rate of change would have been higher. Okay? But this is asking for that particular rate of change at that particular moment. And that's what's new. That's a derivative, that instantaneous rate of change. And notice the units is inches squared per hour. It's a rate. All right, so here's an alternative notation for derivative. So average rate of change is the same. And this is kind of saying I should have an approximation here, because this change in y over change in x is technically still the average rate of change. And having it equal to the derivative, if we're picking a point that's super close, remember 2.001 away from 2, then we're going to get a good estimation of the derivative. So that's why I kind of wish I had a little estimation here, squiggly lines. But this Leibniz notation is, here's your derivative, and we're going to rewrite that. Instead of using a delta, we're going to change it to a d here, dy over dx. But it's still the difference in y values over the difference in x values. And in class, I'm going to go off to the side on the board and give you a little Calc AB lesson with the limits, and that's how we're able to get the derivative, is using limits. So in class, we'll discuss that a little bit more. But this dy dx is another way to represent the derivative. Okay. Another way to write it is you can pull that d dx off here to the side, so d dx of y, and that's the derivative with respect to x of y. So this and dy dx are two ways that we can represent the derivative. Okay, and if I wanted the derivative at a specific number, like 3, f prime of 3, you would write dy dx and then put a bar at x equals 3. And if you go across the world to somebody in a different country that knows how to do calculus and you show that person this notation, that's the awesome thing. They'll know exactly what you're trying to do and what you're getting at. So think of dy dx as a very small change in y divided by a very small change in x. And that's what we'll discuss in class with the whole limits. All right, so now let's interpret the derivative a little bit more. You will have to do this a lot and with a lot of problems in your homework. So the profit, there's that pi symbol, from selling x units is given by this function. Okay, so what are the units of the derivative? So that's the change in y over the change in x. So dollars is your y per unit, dollars per unit. And units are, of course, your x. So what is the practical meaning of the derivative? Well, it's the increase or decrease in profit per unit. And then what is the meaning of, okay, so this is what's new. f prime of 30 equals 250. So what is that? Well, this is the derivative at 30. This is the instantaneous rate of change when x is 30. So at 30 units, we notice that it's positive, so we're increasing by $250 per unit. Okay. And then if f of 25 is 3,500, the derivative at 25 is 175, estimate f of 27. Okay, so let's start with what we know. We know at 25 units, we're making a profit of 3,500. So then let's stay along, let's keep with what we know with the data. So if the derivative at 25 is 175, now if we were in class, I would draw you a picture. We're going to stay along that tangent line. And even though we know it's not totally accurate, at least we know we'll at least be close. So here, let me go grab a whiteboard real fast. Okay, I grabbed a whiteboard. So if this was our profit function here, this curve, and we know at 25, we're making a profit of 3,500. All right. And we know the slope of the tangent line is 175. So what we'll do is to estimate what we think the profit will be at 27, so 2 units over, we're going to stay along that tangent line. So we're going to add the slope 2 times because we're 2 units away, 25 to 27. So we'll stay along that tangent line and we get 3,850. But realize that's along the tangent line. It's a little bit off of our curve, but at least it's an estimate. You'd be able to go to your boss and give a slight overestimate and have an idea, all right? But this is called the tangent line approximation, where you stay along the tangent line to at least give an estimate, which you can see would be really beneficial in the business world. Okay. All right, so here's another example, and this is the same interpreting data and what they're asking for. So P of H be pressure in dynes per square centimeter on a diver at a depth of H meters. Give a practical interpretation in units for each of the following. Okay, so this is your pressure at 100 meters. Here's your instantaneous rate of change, so rate at 100 meters. H such that P of H equals this. So that's that H right there. That's the depth when the pressure is 1.2 times 10 to the 6th. And then this would be your pressure at 10 meters lower in the water. See how the signs have changed? This must have been negative. And then H such that P prime of H equals 20. So when the rate is 20, H would represent the meters when the rate is 20. So just understanding the new notation, getting used to this whole P prime, F prime stuff. Okay. All right, and then, okay. So I called this the tangent line approximation. It can also be called the local linear approximation or linear approximation. I don't ever say the word local. So linear approximation or tangent line approximation. That's what I think what we call it in Calc AB. Same thing. So y equals f of x and the change in x is near 0. So notice and you can see on our picture here, if your change in x, it was only 2, so it's not that bad, but if your change in x is 100, you're staying along the tangent line is not going to be a very good estimate of what's going on along the actual curve. So that's what they're saying by make sure your change in x isn't too big or it's not going to be very beneficial. But notice, here's what you know. That's the data that you know, plus the derivative times the change in x. So in our problem we just did, it was the 3,500 plus our derivative, I think it was 175, times the change in x was 2. And we were able to at least get an approximation. Okay. So same thing here. Suppose f of t is a function. Notice they give you a data point to start with. They give you a derivative, slope of the tangent line, and they want us to estimate these two values. So start with what you know, 4, and then your derivative or your change in x. It doesn't matter which one you do first. It looks like I did the change in x because we went from 3 to 4. So that's a positive 1 times the derivative. Same thing here. Start with what you know, and then in this case, the change was from 3 to 7, so that's 4 units times the derivative. Notice I put a star by those. Almost always there's a question like this. definitely on the midterm and usually on the final exam. Okay. All right, and then our last big topic is relative rate of change. So the relative rate of change at t equals a is defined to be the derivative over the function value. And back in chapter 1, we did related change, relative change. We called it relative change, sorry. Relative change was back in chapter 1. This is called relative rate of change, and it's the derivative, which is a rate, over the original function value. Okay, so in chapter 1, it was just a percent change. In this case, it's actually a rate. It's a percent rate of change. So we'll have to be careful. You'll notice when we do the problem how we put the unit. So this is slightly different. All right, so Carmel High School population can be modeled by C equals F of T, where T is the time in years since 1990 and C is the population. Interpret the statements. F of 18 equals 4,170 and the derivative at 18 is 170. Okay, so I'm going to move my picture up here so we can see. All right, so in 2008, since we started at 1990, we're at 4,170 students. And then this is the rate of change. This is our derivative. So in 2008, it's positive, so we're increasing 170 students per year. All right, now here's what's new. Calculate the relative rate of change, so the typo, of C at t equals 18. Okay, so it's the derivative, which they gave us. There's the 170 over the function value at 18. So once you get that decimal, we do still, same as in chapter 1, we'll move the decimal over 2 spots. So we say increasing 4.08%, but here's what's different. In population per year. In the chapter 1, we would have just said increasing 4.8%, 4.08% and been done. Okay, so derivative over function value. That's the relative rate of change. Okay, I think that's it. Email me if you have any questions and make sure you're doing your homework.